going on to section 2.8 through 2.10, and the topic of this section is hydrostatic forces on plane surfaces and on curved surfaces. Basically what we're dealing with here is if you have an object that is submerged in a fluid, that we understand, of course, that there is a pressure associated with different points on that surface, but that there is some sort of a composite force as well. So I refer you to this diagram that is in your textbook, or a similar diagram is in your textbook anyway, and I want to explain it a little bit. First of all, you'll notice that at the top of the diagram it shows the free surface, and you'll also notice the little triangle at the top on the left hand side indicating that we're in contact with the atmosphere. Then what we have, if you move down through the blue colored fluid, water I would presume, we have a plate, and this diagram is two-dimensional. In other words, Z is up and Y would be over. Now coming out of the plane of the page, we have the x-axis. So in the lower right-hand part of the diagram, you see sort of a blob, the classical potato diagram. And what that really is just indicating that there is an arbitrary shape of this diagram, of this plate, that's being represented in the diagram. So in other words, the potato is what we're seeing in cross-section at the lower side of the triangle representing the water. So it's the cross-section of this submerged plate. So if we continue to look at this, what happens is if you think about this, I'm going to put this on the document camera from your book. Even though I like this diagram quite well, I can't actually point to items on it. So I'm going to put the document camera back up. All right, and so this is in your textbook on page 62. It's the same diagram. But basically, what you see here, free surface, that I was saying, here we are in contact with the atmosphere. We have this depth, which is called h sub c, this depth, which is called h, and here we have a differential force dF acting on a differential area dA. So this is the zy representation, zy representation of the plate, and this is the yx, and those axes are actually labeled of this plate. So that if I took this plate and I turned it sideways, that I would see this. So this little spot the dF is acting on actually corresponds to dA of the potato-shaped plate. Now, you see there are 2 points labeled C and C sub P, or CP. C is the centroid of the plate, and CP is called the center of pressure. That is where the resultant force acts. If you think about this, there's a different force acting on this point than there is on this point. And there's some sort of an integrated function that's going to take us so that we could take all of the little dFs and sum them at the limit, at the calculus limit, so that we could come up with a single F sub r, or resultant force, that indicates not only the magnitude of the force, but the placement or the location of that force, and that's at the center of pressure. Now, oftentimes, atmospheric pressure will cancel itself out. Not always, but if you look, for example, on this is like a fish tank. And what you can see is we have a resulting force, we have an atmospheric pressure, and then underneath we have the same atmospheric pressure acting on the bottom of the tank. So the atmospheric pressure on the top and the bottom cancel itself out because it's equalized in terms of this plate, and the resultant net force is just the weight of the water. Although, of course, in this case it's simpler because it's just gamma times h, or a rho gh problem. All right, so one of the things I wish to refer you to, and you can read about this in your textbook, and I've put some notes along in my textbook, which I'll put up on the screen in just a moment, to sort of help you along. But what we're looking at is a force and a distance to the force. And so from statics, you probably know that what we're discussing here would be a moment. And specifically, we're going to be dealing with first moments of area and second moments of area, which are also known as moments of inertia. So in order to find the placement of the force, and this would be what we call a tipping point. So for example, if you had a gate and you needed to balance it or to tip it open against a hinge, you would need to know these, you would need to have an idea of not only the resultant force, but also where the resultant force occurs so that you can overcome it with a tipping moment. All right, so in your textbook, you see we talk about the magnitude of the resultant force, and it's a function of h sub c, which is the distance to the resultant force. And as it tells you in the margin that the magnitude of the resultant force is equal to the pressure acting at the centroid multiplied by the total area. All right, so these are just some geometric ideas to give you an idea of what those values are going to be. But primarily, some of the things in terms of computation that you'll need to be aware of. Let me telescope this in a little bit. Okay. And then, yeah, the book is a little bit awkward on here. All right. So following along in your own book would probably be the best idea. All right. So we have a magnitude for the resultant force based on the vertical distance from the fluid surface to the centroid of the area. Okay, now remember, the centroid of the area is what we're talking about. So if you refer back to the other diagram, which I'll put up on the computer just a sec. Okay, so there we go. So we're talking about h sub c, which is the distance to the center of pressure, which, as is clearly indicated, is not the centroid. It's actually always going to be below the centroid of the object. Right? So mathematically, we can see that if we take the resultant force and multiply it by our y sub r, which is in the y direction, right? It's the distance along the plate to the resultant force, is going to equal this concept, which is basically a moment of a ydf, which is a moment, isn't it? And if we do the integral of that, we can see that y sub r, the location of that resultant force directed along the plate, is going to be found by the second moment of area, which is called the moment of inertia, divided by ya, which is the first moment. So the integral, and actually it's been already integrated, but if you look at that, that's basically, if you're talking about a line or a rectangle, that's a relatively easy mathematical concept. So the integral in the numerator is the second moment of inertia, and so if we continue with that idea, we can just rewrite the integral of y squared dA over a as I sub x. All right? Now the other thing to remember is I sub x, the moment of inertia, is always a minimum about its own centroid. But we've already stated that it's not going to be about the centroid at all. It's going to actually be below the centroid. So in order to move, if we have tabulated data for moments of inertia about the centroid, which they refer to as IXC, and in statics we call those I bars. So you might call that I bar X or I bar Y, but in this case we're in the X direction, coming out of the page. Then we have an equation for IX about any arbitrary axis using the parallel axis theorem as being the moment of inertia about the centroid plus AY squared, or in statics that was written as AD squared. Okay, so this term in statics looked like this, but it's the same idea. So what this actually does is gives us an equation that allows us to solve for the location of that resultant force along the surface of the parallel, or along the plate itself. So I'm going to flash back to the podium PC so that you can see this picture a little bit different, a little bit better. And what you can see then is that y sub r is the distance from the free surface of the water, not from the top of the plate, but from the free surface of the water along that intersection to the distance in the y direction to the center of pressure. Okay. All right, so the math is a little bit complicated, but if you look off here in the margin, let me see if I can move this a little bit. Oh, that's all I got. All right, so I've written some of the variables down for you, and it's a little bit hard to get them all on the screen. Let me see if I can widen this out a little bit. There we go. Okay, so y sub r is the depth to the resultant force, which is what we're looking for at this particular point. Y sub c is the distance to the depth of the centroid along, remember y is directed, y isn't up and down vertical, y is directed along that surface. So we're talking about the coordinate directions in figure 217. So y sub c is the depth, I guess I would call it, to the centroid. And then we have I sub xc, which is the moment of inertia about the centroid, I sub x, which is the moment about another axis, and in this case we're interested in the axis at the center of pressure, so we can know where the force acts and its magnitude. And this is all on the plane containing the surface and the free surface. The other thing to note is y sub r, this is what I said before, but mathematically we can see it here. Y sub c, which is the depth of the centroid, is equal to this term plus y sub c, or y sub r is equal to this term plus y sub c. Now we know that a moment of inertia is always a positive number, and unless we have a cutout, a is always positive, as is y sub c. So that means that the value for y sub r is always greater than the value for y sub c, meaning that the center of pressure is always below the centroid if this value is not equal to 0. Which it's not, and it will never be negative. All right, so the math is a little bit tricky on that one, but if you just follow through the steps, you'll be all right. Now, there's one other picture that I wanted to show you, and these are some of those values for different shapes. We have a rectangle in the upper left-hand corner, a semicircle below it, a circle off to the right, a triangle below it, and a quarter circle. And the reason that we look at these shapes and that we have the IXC and the IYC and so forth is and the areas are because these are the shapes of common submerged objects. Now, if you go back to the integral form of those equations, you can see that any submerged shape would be fine. You could integrate for any submerged shape. But the geometric properties of some common shapes will probably get you pretty far as the work that you'll be doing in this class. So continuing with some of these ideas before I work a problem for you. Here we go. The point through which the resultant force acts is called the center of pressure. So the center of pressure is, as we said, below the centroid of the plate, or the object that is submerged, and it is the point where the resultant force acts. And it's a resultant hydrostatic force. So if you have, just real briefly kind of simplify this, if you have a free surface of water and you have a submerged plate, regardless of the shape of that plate, at some point you have all of these little DF forces, just differential forces, and they increase because of the hydrostatic gradient, don't they? So the force here is different than the force here. So the resultant force is called F sub r, and it acts at a point, if we're going along the plate, called y sub r. Now, y direction is like this, of course. Okay? And if we're going in a vertical direction from here to here, that's actually a z, but they call that h. Right? So h is actually the distance from the free surface in a vertical sense down to that, well, down to wherever we're talking about f sub r acting. Okay, so it's just kind of important to keep your variables straight on this type of a problem. The book explains it very, very well, but I'm not really sure how readily familiar you are with the moments of inertia and the first moments from your time in statics. All right, so the next concept then, here is the next concept in section 2.9 is called a pressure prism. And a pressure prism is a geometric representation of the force acting on a submerged surface. Okay, so the pressure prism is the force acting on a submerged surface. Now, the first thing that you need to remember is if we have a fluid and we have something submerged in it, and if there's any shear force at all, in other words, if there's anything that is not perpendicular to the surface of that submerged object, whatever it is, the fluid is going to start to move. So we're not talking about anything except for normal or perpendicular forces. So when we're talking about hydrostatic force, we're always talking about something that's still, and by virtue of the behavior of fluids, then it has to be oriented perpendicular to the object. So if we have a pressure prism, if we have a free surface that looks like this, and we have a plate that is submerged. Okay. Now we know, let's say that this is H1 down to the top of the plate. In other words, the plate is beneath, the top of the plate is beneath the surface of the water. At this point, our gauge pressure from our hydrostatic pressure is going to be 0, isn't it? And if we're talking about something that has a constant specific weight, then the pressure is going to look like this. Okay, in other words, the pressure is going to be equal to the surface pressure or to the free surface pressure at the top. But by the time we get to the top of the plate, it's equal to gamma times H1. Right? Because that's just hydrostatic. Then down here, if we call this entire depth H2, the pressure down here is going to be gamma times H2, and the pressure prism, if we look at this, is going to start here and end here. In other words, it's not going to be pointy at the top, but it's going to have a magnitude equal to gamma times H2 minus H1. Right? All right, so if we then look at how that pressure prism affects the work that we do, we can analyze the force, Analyze, the force, the hydrostatic force, just using the concept we developed last time of pressure equals force divided by area, pressure times area equals force. And so if we can find the pressure, the area, essentially, of the pressure prism, we have a pressure times an area, and that will equal the resultant hydrostatic force. So that's pretty simple. That breaks it down to a pretty analyzable problem. Now, the other part about this is where does that force act? Well, it acts, as we said, not at the centroid of the plate, but at the centroid of the pressure prism. So once again, we're dealing with a geometric representation of the hydrostatic force. But even though the point where the hydrostatic force acts is going to be below the centroid of the actual object that's submerged, it will be at the centroid of the pressure prism. And one of the problems that you're going to do for homework, problem 252, spells this out very carefully. So if you, when you're working with problem 252, you can use the example in the book, example 2.7 and example 2.6. Use example 2.7, 2.6, and 2.7 to go through that problem, and it will give you sort of the mechanical basis of getting that done. Now, the last section that we cover in this vodcast is the hydrostatic force on a curved surface. And after you've developed this technique of creating a pressure prism, you can use it to do any sort of a surface. But if you have a curved surface that's submerged, you can recall that since all of the forces have to be perpendicular to the surface, that your forces are going to look something like this. If you had, that's just a quarter circle. But the forces, or the pressure prism, is going to look like that. So if you take a look at the diagram in your book again, you can choose the type of curved surface that you have, whether it's a circle, semicircle, or quarter circle, and use this analysis technique in order to develop your equations for those shapes as well. All right. Now, the next thing I'm going to do for this section is to do problem 251 for you, to give you a guide for how to work some of these problems. And this one is kind of an interesting problem because it shows an open tank. It's an open tank of water, and we have a 6-foot diameter conduit with a circular plug used to seal that conduit. And I kind of like this problem for a number of reasons. One is it helps you to understand this whole it's not even zy, it's actually y is, well, let's just leave it like that for this problem, and x. So when we have a coordinate system like this, and x is coming out of the board, what we have is this tank of water, and we have a conduit that is 9 feet. The top of the conduit, which is referred to as the invert in, is 9 feet below the top, the free surface of the water. Right? And we have a plug, which we're told is circular. But in this problem, of course, it doesn't look circular. It looks like it's a rectangle. But when we say it's circular, what do we mean? Well, we mean that if we bring out the dimension, in other words, if we flip it out 90 degrees, we take that and we flip it, we would see a circle. So in other words, the cross-section of this is circular. And I kind of like that because I think that that is something that can be a little bit hard to ascertain on the sideways, non-oblique, or I guess they would be oblique diagrams that they show you for the x, y, and z coordinates. All right, so basically we have a large open tank, contains water, and it's connected to a 6-foot diameter conduit. A circular plug is used to seal the conduit. Determine the magnitude, direction, and location of the force of water on this plug. Okay, so we know a couple of things. We know that we're looking for F sub r, the resultant hydrostatic force. We also know that it's going to be perpendicular to the surface of the plug, because if it wasn't, it would not be static. And although we have a circular area, we definitely have just a straight up and down surface that this is acting on. So the surface itself is not oblique within the water, but it's just a straight up and down line as far as the hydrostatic force goes. All right, so let's find out. What's the magnitude? Well, F sub r, our resultant force, is equal to gamma times h sub c times the area. And gamma for water is 62.4, or it's about 62.4 pounds per cubic foot. And what is our depth? Well, h sub c is the centroid of the plug. So we are at 9 feet plus half of the plug, so 9 plus 3, which is 12 feet below the surface of the water, times the area of the plug. If the plug is 6 feet in diameter, as we can see from this picture up above, we can either say that the area is equal to either pi r squared or pi d squared over 4, and either way is fine. But if we take pi times d squared in feet over 4, what we see is we have feet squared feet, feet. So we have feet to the third on the bottom, feet to the third on the top, and it cancels out. So we get the magnitude of our resultant force is, did I bring my calculator today? Okay. So we have a magnitude of, let me clear this off. There we go. 62.4 times 12 times pi times 6 times 6 is 36 divided by 4, and that gives me a magnitude of 21,161 pounds. 21,161 pounds. I have a few too many significant figures there, but I'll leave it for just a moment. All right. Now, where is it located? What is my y sub r? In other words, what's the placement? Where is that going to be? Well, from my equations, I know that that's going to equal I sub xc, moment of inertia of a circle, about its centroid, divided by y sub c times a plus y sub c. All right, so if I look at the information for a circle, I know that I sub xc for a circle, and this is on the material that we've already covered. I mean, you've seen it on the screen. It's equal to pi r to the 4th over 4. Maybe I should show that to you. Hang on just a second. All right, so just so that you see it, I'll put it back on the podium PC. And there you go. So if you look up in the top right, you'll see I sub xc, the second equation down, is pi r to the 4th over 4. Okay. So if I solve for that, I get pi times my radius. If my diameter is 6 feet, that's 3 feet. So that's 3 raised to the 4th power over 4. And 3 to the 4th power is just 3 squared times 3 squared, which is 9 times 9, or 81 feet to the 4th. So I have pi times 81 feet to the 4th over 4. And if I do the math on that, divided by 4. That gives me an I sub xc value of 63.6 feet to the fourth. All right. So continuing with that line of thought, we want to take y sub r, which is equal to I sub xc, which I have as a value of 63 point, my calculator actually told me 585, so I'm going to keep too many significant figures in it for just a moment, divided by y sub c, which is going to be 9 feet plus 3 feet, or 12 feet, times the area of my circle, which is pi times d squared over 4, or pi times the radius squared. And I'm going to check my units in just a minute, plus y sub c, which is 12 feet. All right, so this is feet to the fourth. I have feet, and feet squared is feet to the third. So this cancels this, and I'm left with units of feet. Okay, so I have feet to the fourth divided by feet, and divided again by feet squared, which is feet to the third, and add that to feet. So my value of y sub r then is this number, 63.585 divided by 12 divided by pi, and divided again by 3 squared, which is 9. All right, and that value actually, I only divided that by 3. I need to divide it by 3 again. Yeah, there we go. Y sub r is equal to 0.1875 plus 12. Now I wanted to show you this value of 0.1875 plus 12 because remember, this is my centroid, and my center of pressure is always going to be below the centroid, so the 0.1875 feet is how far below the centroid the center of pressure is. So my y sub r value is 12.1875 feet. All right. So the answer is that I have a force, let me just write this down, therefore my resultant force of, it says 21,161 pounds, 21,200 pounds, acts 12.19 feet below the water surface. And then it asks the direction, and the direction has to be perpendicular to the plug surface. Okay, so I've answered all 3 of those questions. All right, so that's it for sections 2.8 through 210, talking about hydrostatic force, the location of the hydrostatic force, and the magnitude of the hydrostatic force. You may need a little brush up on working with moments of inertia, but the rest of it should come pretty quickly, and especially if you think about the way that this is developed. We can do a strict mathematical development, or we can do more of a kinesthetic or geometric development, but we still come out with the same answer. So there you go. All right, we'll see you for the next lecture, Vodcast number 8, which will be about buoyancy, and we'll finish off chapter 2.